Good afternoon, everybody. Thanks for joining us. Just want to throw out a couple of housekeeping tips. We usually reserve the final 15 minutes for Q&A. You can use the Q&A button to submit your questions. It's usually found at the bottom of your screen. We also, if you'd like us to open your microphone, just use the raise your hand button and I will unmute you. Thanks. Okay. We have another great talk in store. Today's security seminar will be presented by Professor Neil Gong. Neil is an assistant professor in the Department of Electrical and Computer Engineering and the Department of Computer Science at Duke. The focus of his cybersecurity research is in privacy and machine learning. His talk is titled Secure Federated Learning. Neil, welcome to CERIAS Summer Security Seminar. You now have the Zoom floor.
Okay. Yeah, thanks for the introduction, Mike. Hello, everyone. I am Neil Gong. I'm assistant professor at Duke. Today, I will talk about our work on secure federated learning. Before getting started, I'd like to thank the CERIAS Center for giving me the opportunity to present this talk. As you may know, centralized learning is a popular conventional machine learning paradigm. Suppose we're given some clients. These clients could be smartphone, IoT devices, or self-driving cars. Each client has some data locally. In centralized learning, these clients send their raw data to a cloud server, which is managed by a service provider such as Google, Apple, and Facebook. The service provider then uses the client raw data to train a machine learning model, and the model is used to provide services for the client. However, such centralized learning faces multiple challenges. For example, the first challenge is that the server may be vulnerable to data breaches due to various network and system vulnerabilities. It was reported that over the past 10 years, there have been 300 data breaches involving the theft of 100,000 or more records. These data breaches put client data security and privacy at high risk. The second challenge is that centralized learning incurs high communications costs, which may be intolerable for resource-constrained clients, such as smartphone and IoT devices. Federated learning is an emerging machine learning paradigm to address the challenges of centralized learning. Specifically, in federated learning, client data stay locally on themselves. Each client trains a machine learning locally, and the client sends their models or model updates instead of their raw data to the server. Federated learning has been widely deployed by internet giants. For example, Google uses federated learning for the next word prediction on a virtual keyboard app called Gboard. Apple uses federated learning to personalize Siri. While there are already many studies on improving the accuracy and reducing the communication cost of federated learning, its security aspect is much less explored. So in this talk, we will discuss the security aspect of federated learning. In particular, we will discuss the following two questions. The first question is, what are the security issues of this emerging federated learning paradigm? After understanding these security issues, we will then discuss the second question, that is, how to build secure federated learning to address the security issues. This is a roadmap of this talk. In part one, we will discuss our local model poisoning attacks to federated learning. In part two, we will discuss how to build secure federated learning via bootstrapping trust on the server. And in part three, we will discuss our work on building provably secure federated learning. So first, let's look at part one. Before introducing our attacks, I'd like to describe a little bit more technical background about federated learning. We are given some clients each client has some data locally. We also have a cloud server. The server maintains a machine learning model called a global model. Each client also maintains a machine learning model called local model. Then federated learning is an iterative process, and in each iteration, federated learning performs the following 3 steps. In step 1, the server sends the current global model to the client or a subset of them. In step 2, the client trains their local models based on the current global model and their local data. For example, client I may initialize its local model Wi as the current global model W. And then client I uses stochastic gradient descent to update its local model Wi. Here alpha is the learning rate. Gi is a gradient of client I's local loss with respect to its local model Wi. Each client can repeat this stochastic gradient descent for multiple steps locally. Then the client sends their local models to the server. In step 3, the server aggregates the client's local models as a new global model. For example, in a federated learning method called Fedaverage, developed by Google, the global model W is basically the average of the client's local models. So federated learning basically repeats these 3 steps for many iterations, and the final global model is used to provide services for the client. We note that it is equivalent to send local model update Wi minus W instead of the local models Wi in step 2 to the server, which we will use in part 2 of this talk. Federated learning is basically a distributed system. And due to its distributed nature, it is fundamentally vulnerable to poisoning attacks. Specifically, an attacker may have access to some malicious clients. These malicious clients could be fake clients injected by an attacker into the federated learning system, or genuine clients compromised by an attacker. A malicious client can poison its local data, which is known as data poisoning attack. A malicious client can also directly poison its local model, which we call local model poisoning attack. Eventually, the global model is poisoned, and the poisoned global model makes incorrect predictions as the attacker desires. For example, a single malicious client can arbitrarily change the global model learned by Fedaverage, which we just described in the previous slide. To defend against these poisoning attacks, the machine learning community has actually developed multiple Byzantine-robust federated learning methods. Recall that federated learning has 3 steps in each iteration. These Byzantine-robust methods essentially use Byzantine-robust aggregation rules in step 3, instead of the average aggregation rule used by Fedaverage. Roughly speaking, the key idea of this Byzantine-robust method is to remove outlier local models before aggregating them as a global model. Under some assumptions, for example, the client's local data are IID and the loss function is smooth and so on, these Byzantine-robust methods can even bound the change of the global model parameters caused by malicious clients. Next, I will use median as an example to illustrate how Byzantine-robust aggregation rule works. Suppose each local or global model has n parameters, and these are the n parameters of client 1's local model in some iteration. And these are the n parameters of client 2's local model in some iteration. And these are the n parameters of client n's local model. And these n local models are sent to the server, and the server aggregates them to obtain a global model. Specifically, the server calculates the median of the n first parameters of the n local models as the first parameter of the global model. The server calculates the median of the second parameters of the n local models as the second parameter of the global model. And the server repeats this operation to calculate the n parameters of the global model. Our work basically shows that these Byzantine-robust federated learning methods are still vulnerable to local model poisoning attacks. In particular, an attacker can still substantially increase the testing error rate of the global model learned by a Byzantine-robust method. Recall that these Byzantine-robust methods can have nice theoretical guarantees based on some assumptions. However, they are still vulnerable to our attacks because those assumptions often do not hold. And even if those assumptions do hold, they cannot bound the change of the testing error rate caused by our attacks, because they can only bound the change of the global model parameters. We consider the following threat model in our attacks. An attacker's goal is to increase the testing error rate of the global model. An attacker has access to some malicious client, which could be fake client injected by an attacker or genuine client compromised by the attacker. These malicious clients can send arbitrary local models to the server. In terms of the attacker's background knowledge, we consider both full and partial knowledge scenarios. In the full knowledge scenario, an attacker has access to the local data and local models on all clients. In the partial knowledge scenario, the attacker only has access to the local data and the local models on the malicious client. As you can imagine, the full knowledge scenario may be unrealistic in practice. So we use this full knowledge scenario to estimate the upper bound of our attack's threat. The attacker may or may not know the aggregation rule used by the server. Next, I will introduce the key idea of our attack. Suppose W previous is a global model in the previous iteration. And for simplicity, let's assume we only have two clients. W1 is a local model on client 1 in the current iteration. W2 is a local model on client 2 in the current iteration. These two local models are sent to the server, and the server aggregates them to obtain a new global model W in the current iteration. So when there are no attacks, the global model changes along some direction like this in two consecutive iterations. Our attack idea is to deviate the global model the most along the inverse of this direction. For instance, in this example, we aim to deviate the global model W to be W prime. Let's assume client 1 is malicious. And in order to deviate the global model to be W prime, client 1, which is malicious, sends a poisoned local model W1 prime to the server, such that the aggregation of W1 prime and W2 becomes W prime. Technically, we formulate our local model poisoning attack as this optimization problem. The objective function is to maximize the deviation of the global model in some iteration. W is a global model before attack. W prime is a global model after attack. S is the update direction of the global model before attack. Without loss of generality, let's assume the first C client are malicious, and the W1 prime, W2 prime, until WC prime are the poisoned local models on the malicious client. So our optimization problem aims to find the optimal poisoned local models on the malicious client to maximize the deviation of the global model. This constraint means that the global model W before attack is an aggregation of the local models on the benign client, where this A is an aggregation rule. This constraint means that the global model W prime after attack is an aggregation of the poisoned local models on the malicious client and the benign local models on the benign client. So in our attacks, an attacker basically solves this optimization problem to find the optimal poisoned local models in all or multiple iterations of federated learning. We note that our formulation is applicable to any aggregation rule. So in the future, if a new aggregation rule is proposed, our framework can be adapted to evaluate its security. So next, I will briefly discuss how to solve the optimization problem, and the details can be found in our paper. In a full logic scenario, the attacker has access to the local models on all clients, and we can just solve the optimization problem using them. In the partial logic scenario, the attacker only has access to the local models on the malicious client. We use them to estimate a global model W, and then solve the optimization problem based on the estimated global model W. When an attacker does not know the aggregation rule used by the server, the attacker can assume one aggregation rule and then solve the optimization problem based on the assumed aggregation rule. As we will see soon, our attack constructed based on one aggregation rule will also be effective against other aggregation rules. In our experiment, we assume there are 100 clients in total, and 20 of them are malicious. We evaluated our attacks on multiple data sets. A unique characteristic of federated learning is that the client local data are often long-IID. Therefore, we distribute a data set to the client such that the client's local data are long-IID. Next, I will show you some experimental results on MNIST, which is a popular benchmark data set in machine learning. The results on the other data sets can be found in our paper. This table shows the results of our attacks and the multiple baseline attacks. Each row corresponds to a Byzantine-robust federated learning method. This column means low attack. This column means adding random Gaussian noise to the local models on the malicious client. This column means flipping the labels of the local training examples on the malicious client. This column means our attack in the partial knowledge scenario, and this column means our attack in the full knowledge scenario. The numbers in this table are testing error rates of the global models learned by different methods under different attacks. For example, this number, 0.75, means that the global model learned by Chrome under our attack in the partial logic scenario has a testing error rate of 0.75. So as we can see from this table, our attacks can significantly increase the testing error rate of the global models learned by Byzantine-robust methods. This figure shows the impact of the fraction of malicious clients on the attack effectiveness. The x-axis is the fraction of malicious clients, The y-axis is the testing error rate of the global models learned by Chrome. Different curves correspond to different attacks. As we can see, our attacks are more effective when more clients become malicious. This figure shows the impact of the degree of long IID of the client local data on the attack effectiveness. The x-axis is the degree of long IID of the client local data. The y-axis is the testing error rate of the global model. And the different curves correspond to different attacks. As we can see, our attacks are more effective when the client local data are more long IID. By the way, the details about how we simulate different degrees of long IID can be found in our paper. This table shows the results when the attacker does not know the aggregation rule used by the server. Specifically, this column means that the server uses Chrome as the aggregation rule. This column means that the server uses trimmed mean. And this column means that the server uses medium. This row means low attack. This row means that the attacker assumes the server uses Chrome and performs attack based on Chrome. And this row means that the attacker assumes the server uses trimmed mean and performs attack based on trimmed mean. Again, the numbers in the table are the testing error rate of the global models. As we can see from this table, our attack constructed based on one aggregation rule is also effective against other aggregation rules in most cases. This table compares our local model poisoning attacks with data poisoning attacks. Recall that data poisoning attacks poison the local data on the malicious clients, while our local model poisoning attacks poison the local models on the malicious client. This column means no attack. This column means the state-of-the-art data poisoning attack. And the last two columns correspond to our attacks in the partial and the full launch scenarios, respectively. Each row corresponds to a Byzantine-robust method. Again, the numbers in the table are testing error rates of the global models under different attacks. First, data poisoning attacks are ineffective for Byzantine-robust methods because this column is almost the same as this column. Second, our attacks are effective for Byzantine-robust methods because these two columns have large testing error rates. To summarize a little bit, we proposed a general framework to attack federated learning. Our results show that existing Byzantine-robust federated learning methods are vulnerable to local model poisoning attacks. So that is part one of this talk. And I think I saw some, okay, link to the paper. Okay, thanks, Mike, for the link to the paper. So maybe I can pause to see whether we have any questions about part one of this talk. Yeah, do we have any question or comments about part one?
Yeah, Neil, hold just a second. I have some hands being raised here. So I'm going to start in order. Saurabh, nice to hear from you. Go ahead. You have the mic.
Hi, Neil. Can you hear me?
Yes.
Yes, I can hear you.
So the last part of what you presented with the data poisoning versus your model poisoning attack, can we generalize from that and say that data poisoning is strictly a weaker attack form for federated learning than model poisoning?
Can we, are you saying like or some fundamentally or theoretically we can?
Yes. For federated learning can be once and for all safe. If our scheme is resilient against model poisoning, then by definition it is resilient against data poisoning.
I'm not sure. I think so. First, I think for so I can have the following comment. So for any data poisoning, I think it's very easy to transform it into a local model poisoning. So basically, for any data poisoning attack, we can easily design a local model poisoning attack, which has exactly the same effect as a data poisoning attack, but not a vice versa, probably. Because you see, if we want to have a specific local model, we have to reverse that local model back to how are we going to poison the local data to have that specific local model. So to summarize a little bit, we can easily we can easily transform any data poisoning attack to be a local model poisoning attack, but probably not that easy to go in the other direction. And for your question, if we can prevent model poisoning attacks, does that mean we can also prevent all data poisoning attacks? I think it depends on your defense. It depends on your defense. If your defense, for example, if a defense does not have provable guarantee, does not have theoretical guarantee, then it may not be the case. Because if you say, if we come up with a defense, this defense can empirically defend against some local model poisoning attacks, okay, some specific local model poisoning attacks, then that defense may not be able to defend against some very advanced data poisoning attacks. But if the defense has theoretical guarantee, which means that if the defense can defend against all possible local model poisoning attacks, like whatever, however you change the local models, you construct the poison local models, your defense is secure. Then I think that defense is also secure against the data poisoning attacks.
So quick follow-up. So such a defense does not exist today, right? Something that is resilient against all local model poisoning attacks.
Actually, in part 3, I'm going to discuss that a little bit. Yeah.
I see. Okay, great. Thank you.
Yeah, thank you. Let's see. I think we have other.
Yeah, I have another hand raised here. Richard, if you'd like to ask.
Yes, sure. And I've typed my question in the Q&A as well.
Okay.
Thank you very much for your talk. It's been great. What percentage of compromised clients are needed to achieve greater than 0.5 testing error rate?
I think this question depends on the data set and the specific federated learning setting. Yeah, like probably we can go back to some slide here. So here.
Okay, there we go.
Yeah, the x-axis is a fraction of malicious clients. Yeah.
So anything over 5%.
Right. This is, but this is for full knowledge attack. If we look at the partial knowledge attack, it's around like 10%.
Yes. Okay.
But this is also for this specific method called Chrome. Yeah. And these curves may be different for different methods. Yeah.
That's not very many.
Yeah. Yeah. And also these clients may not be only compromised. They can also be fake clients. Like say I have a computer, I have a powerful computer. I can just use my computer to simulate many like smartphones.
Yep.
Yeah. Okay. Yeah. Thanks for the question.
Thank you.
Yeah. Let's see. Do we have any more questions? Okay. Mutation of attack color case you can defend to invade. Yeah, so let me read. There are some more questions in chat. So what do you think are the limitations of your attack color cases where we can defend to enable silver? Okay. So I think the limitation of our attack, basically, I guess that's what we can discuss in the next 2 parts, in part 2 and part 3. Basically, we can defend against these attacks, and kind of leveraging the limitation of our attack. So probably we can continue. Okay, so let's continue to part 2 about building secure federated learning via bootstrapping trust on the server. So first, the root cause of the insecurity of federated learning is that there is no root trust in the system. Specifically, from the server's perspective, every client could be malicious. Based on this observation, we propose to build secure federated learning via bootstrapping trust on the server. Specifically, the server collects a small, clean training data set itself. The server maintains a local model based on its collected training data set, just like how a client maintains a local model. We call the server's local model server model. Then the server uses the server model to bootstrap trust. Specifically, in each iteration, the server assigns trust scores to the client based on the similarities between the client local models and the server model. And then the server considers these trust scores when aggregating the client local models to a global model. Recall that federated learning has 3 steps. In step 1, the server sends its current global model to the client or a subset of them. In step 2, the client trains their local models. However, unlike what we did in part 1, now we assume the client sends their local model update instead of their local models to the server. In step 3, the server aggregates the client local model update as a global model update and uses the global model update to update the global model. So in our new federated learning method, we basically design a new aggregation rule in step 3. And our new aggregation rule considers both the client local model update and the server model update to update the global model. So next, I will use an example to illustrate our new aggregation rule. For simplicity, let's assume we only have 2 clients. These 2 clients have local model updates G1 and G2 in some iteration. The server model update is G0. This graph illustrates these model updates as vectors in the vector space. Our intuition is that if a local model update deviates substantially from the server model update, then the local model update may be from a malicious client. For instance, in our example, the local model update G2 deviates substantially from the server model update G0. So the local model update G2 may be from a malicious client. Based on this intuition, for each client, we compute a cosine similarity between the client local model and the local model update and the server model update. And we use the rule to clip the cosine similarity as a client trust score. Here, rule basically resets the cosine similarity as 0 if it is negative. And rule keeps the cosine similarity as a trust score if it's non-negative. In our example, for client 1, we first compute the cosine similarity between local model update G1 and server model update G0. Then we use rule to clip C1 as the client 1's trust score TS1. Since the cosine similarity C1 is positive, the trust score TS1 is basically C1. For client 2, we first compute the cosine similarity between G2 and G0. Then we use rule to clip G2 to be the client 2's trust score TS2. Since the cosine similarity C2 is negative, the trust score TS2 becomes 0. In local model poisoning attacks, the local models, the poisoned local models from the malicious client often have large magnitudes in order to dominate the impact of the local models from the benign client. So we also propose to normalize the magnitude of the local model update. Specifically, we normalize the magnitude of the local model update such that they have the same magnitude as the server model update. For instance, G1 bar is a normalized local model update for client 1. G2 bar is a normalized local model update for client 2. Finally, the server computes the global model update G as the average of the client normalized local model update, weighted by their trust scores. And the server uses G to update the global model W. Here, beta is learning rate. Theoretically, we show that under some assumptions, for an arbitrary number of malicious clients, the difference between the global model learned by FL trust and the optimal global model under no attacks can be bounded. Empirically, we evaluated our method on multiple data sets. And in the following, I will show you just one experimental result on MNIST, and the results on the other data sets can be found in our paper. We assume there are 100 clients and 20 of them are malicious. The server's training data set includes 100 training examples sampled from MNIST uniformly at random. This table shows the results. Each row corresponds to no attack or an existing poisoning attack. Each column corresponds to a federated learning method. Here, FL trust is our method, and the Fed average is the state-of-the-art method in non-adversarial settings. Again, the numbers in the table are testing error rate of the global models learned by different methods under different attacks. For example, this number 0.04 is the testing error rate of the global model learned by Fed average under no attack. As we can see from this table, our FL trust is robust against various existing poisoning attacks. In particular, the testing error rates of FL trust under different attacks are similar to the testing error rate of Fed average under no attack. So if we deploy FL trust and an attacker knows that FL trust is deployed, an attacker can design an adaptive attack to FL trust. We call that we formulated our local model poisoning attack as this optimization problem, which is applicable to any aggregation. Therefore, an attacker can construct an adaptive attack to FL trust by replacing the aggregation rule A in this optimization problem as the aggregation rule of FL trust. This is how we construct an adaptive attack to FL trust. This figure shows that our FL trust is also robust against such adaptive attack. The x-axis is a fraction of malicious clients. The y-axis is the testing error rate of the global models. This curve corresponds to Fed average under no attack. And this curve corresponds to FL trust under such adaptive attack. As we can see from this graph, FL trust under the adaptive attack and Fed average under no attack can achieve similar testing error rate when up to 90% of clients are malicious. To summarize, the server can enhance security of federated learning via collecting a small training data set to bootstrap trust. So that is part 2 of this talk. And let's see, do we have any questions about part 2? Okay, let me see Q&A. How the first question is how IID is the data. So we tried in our paper we did a lot of experiments. So we tried the different degrees of long IID. Okay, so we tried the different degrees of long IID. Yeah, and some are highly long IID and some are not that highly long IID. Yeah. So for more details, please check our paper. Yeah, let me see the next question. Hello, when RERU is applied to compute the trust score, what fraction of clients are insured to have a non-zero trust score? If a large number of clients do not have a high quotient similarity with the low data set update, can there be information loss? So the question is, what fraction of clients have non-zero trust score? We don't have any theoretical guarantee about this, but in our and if in some iteration, okay, if in some iteration no clients have non-zero trust score, then we basically don't update the global model in that particular iteration. Yeah. And I agree, if this scenario happens a lot, we may have some information loss. Yeah. Okay, so I hope that answers your question. So let me see the next question. Does bootstrapping handle very high long IID, say higher than 0.6? Yeah, I think this is a very good question. I think so. The question is, again, is about the long IID setting, right? So I think in FL trust, there are two possible places where long IID may happen. One is the client local data are long IID. Okay. The second is the server's training data set may have a different distribution, right? With the client local data. So these two places could have long IID, and they may influence the effectiveness of FL trust. First of all, we don't have any theoretical guarantee about the performance of FL trust under such long IID setting, but we did a lot of empirical experiments, and the details can be found in our paper. So we basically explored one important message is that once the server's training data set is not too far away from the overall training data distribution of the client, then FL trust works well. Okay, but if the server's training data set is very different from the distribution of the client's data, then FL trust will not work well. Yeah. Okay, so I hope that answers your question. Okay, one more question. How often do you then update the bootstrap data set? Okay, so the question is, how often do we update the bootstrap data set? That's a good question. We didn't explore this. We didn't explore this this aspect in our work. But if this is definitely a good question, especially if the data is more like a time series. For example, if data the data distribution, the client's data distribution shifts, for example, in real world, okay, the client's data shifts over time, and then we may also need to update the server's training data set accordingly. And how often should we update? I think it may be application dependent. Yeah, maybe there is some way the server, maybe there is some way for the server to decide when it should update its training data set based on some statistics. Yeah, I think this is a very good question. I don't have a very good answer yet, but I think it's application dependent, and it's very interesting to explore. Like how can the server know when it should update its training data set and how? Yeah, I think that's a very good question. It may be some future work to explore. Okay, one more question. When you perform the normalization and rerule of the local weight, will that impact the model performance at the server, especially when there is no attack? Okay, yeah, this is a good question. And actually our empirical, again, it's empirical. Okay? Our empirical results show that it's actually not influencing the model performance when there are no attacks. One of our design goals is to make sure that our method works as well as Fed average when there are no attacks. Yeah. But again, this is based on the assumption that the server's training data set is not too different from the overall training data of the client. Yeah. But if the server's training data is too different from the overall training data distribution, then we will have performance loss. No. Okay. Okay. Yeah. Thanks for all the questions. So now let's continue to part 3 of this talk about how to build provably secure federated learning methods. So existing Byzantine-robust federated learning methods, including our FL trust, can bound the change in global model parameters caused by malicious clients based on some assumptions. However, these assumptions often do not hold in practice. Moreover, they cannot bound the change of testing error rate or accuracy caused by malicious clients, even if these assumptions do hold. To address these limitations, we propose to build provably secure federated learning. For a given testing data set, our provably secure federated learning can guarantee a lower bound of testing accuracy, no matter what attacks the malicious clients use. And the only assumption our method requires is that the number of malicious clients is bounded. Let's first formally define what we mean by provable security. Suppose we are given a set of benign clients C and a testing input X. We also have a federated learning algorithm H. HCX is a label predicted for X when the global model is trained on C using federated learning algorithm H. Now, assume some clients in C become malicious, and we denote the set of clients, including the malicious ones, as C prime. HC prime X is a label predicted for X when the global model is trained on C prime using federated learning algorithm H. We see the federated learning algorithm H is provably secure if HC prime X equals HCX for any C prime such that the number of malicious clients is at most M star. In other words, a federated learning algorithm is provably secure if its predicted label for a testing input is provably not affected by a bounded number of malicious clients. Here, we define M star as a certified security level for testing input X. Note that different testing inputs may have different certified security levels. We propose an ensemble federated learning method, which is the first method to achieve such provable security. Suppose we are given N clients. We pick K clients uniformly at random and train a global model on them. we can train the global model using any federated learning method, such as Fedaverage. We repeat this operation to train n global models. Given a test input X, we use each of these n global models to predict its label. So we have n predicted labels in total. Then we take a majority vote among the n predicted labels as the final predicted label for X. Next, I will use an example to illustrate why our ensemble federated learning is secure. Suppose we have 5 clients and C5 is malicious. We train 4 global models, W1, W2, W3, and W4. And each global model is trained using 3 randomly picked clients. And the global models W1, W2, and W3 are trained using only benign clients. However, the global model W4 is trained using 3 clients, including the malicious client C5. So W4 is poisoned and may make incorrect predictions. Given a testing input X, the poisoned global model W4 makes an incorrect prediction. However, the global models W1, W2, and W3 still make correct predictions. Therefore, the majority vote among the 4 global models is still correct and is not affected by the malicious client C5, no matter what attacks the malicious client C5 uses. Theoretically, we show that this ensemble federated learning achieves the provable security. Specifically, given a set of client C and a test input X, we can derive the certified security level M star for X. Moreover, we show that our derived certified security level is tight, which means that without making more assumptions, it is theoretically impossible to derive a certified security level that is larger than ours. In our evaluation, we use certified accuracy at M as an evaluation metric. Given a testing data set, certified accuracy at M is a fraction of testing input whose labels are correctly predicted and whose certified security levels are at least N. Certified accuracy at N is a lower bound of testing accuracy a method can achieve when the number of malicious clients is at most N, no matter what poisoning attacks these malicious clients use. In this figure, the x-axis is the number of malicious clients N. The y-axis is the certified accuracy at N. This curve corresponds to Fedaverage. This curve corresponds to our ensemble Fedaverage. In ensemble Fedaverage, we basically use Fedaverage to train the N global models. The results are obtained from MNIST, and we assume 1,000 clients in total. So as we can see, the certified accuracy of Fedaverage reduces to 0 when just 1 client becomes malicious. However, the certified accuracy of ensemble Fedaverage is still larger than 0.85 when 20 clients become malicious. This figure shows the impact of the number of global models on our method. The x-axis is the number of malicious clients N. The y-axis is the certified accuracy at N. Different curves correspond to different N. So as we can see, when we increase N from 100 to 500, okay, which are these 2 curves, the certified accuracy increases substantially. However, when we further increase N to be 1,000, which corresponds to this curve, the certified accuracy increases marginally. So these results show that a moderate number of global models are enough for our method to achieve good certified accuracy. To summarize a little bit, ensemble federated learning is probably secure against a bounded number of malicious clients. And our method can achieve certified accuracy, which is a lower bound of testing accuracy no matter what attacks the malicious clients use. So in this talk, we discussed local model poisoning attacks to federated learning and how to build secure federated learning via bootstrapping trust on the server and ensemble methods. Finally, I'd like to thank my students and the collaborators in this research. So that concludes my presentation. Yeah, and let's see, do we have more questions? Okay, so Richard has one more. It's not like a question, it's a comment. Maybe update at the rate of change of the long zero.
That is to say, update the server model.
Yeah.
That was part 2.
Right, part 2. Yes. That is update the server model or the server's training data set or something.
Yes.
Yeah, I think that's a good suggestion. Yeah, I do think this is a very interesting direction, actually, how to update the server's training data set. Yeah. Okay, yeah, thanks for the comment, Richard. Yeah, let's see, do we have more questions? Okay, yeah, seems like we don't have any more questions.
Yeah, I have some hands raised here.
Okay.
Somali, I'm gonna turn on your microphone.
Can you hear me?
Yes.
Yeah.
Hi, I'm Shamali Chatterjee. I'm an assistant professor at Purdue University, and that was my comment about updating the bootstrapped model. I think this was fantastically delivered. You had the attack, and then you showed how we can defend against a very malicious attack. So for the second point, where you have this ability to bootstrap the server model by bootstrapping what you have in terms of the clients exposing different kinds of IID or non-IID data sets, do you think that is kind of going against the very philosophy of federated learning, especially if you start kind of innovating and updating that bootstrap model? Does that kind of go against the fact that in federated learning, we don't want to do too much of that? So if you start trying to improve the accuracy of that bootstrap model, you might be exposing more of the data sets from the clients.
You might, so let me make sure I understand your comment. But the server's training data set is not from the client. The server collects the training data set by itself.
I see. So yeah, and that was my other question. How do you finesse that bootstrap data set at the server? Like, would it be kind of a snapshot of what the clients are sending? So I guess there is like kind of a tug of war there. How would you collect something that is representative without kind of intruding into the data space?
Yeah, that's a good question. So first of all, I think the server should not collect the data set from an untrusted client, because otherwise the server training data may be poisoned. It's like a data poisoning. So we argue that the server should collect a clean, not poisoned training data set by itself. Next, for example, Google. Let's say we use a MList, the handwritten digit recognition as an example. Okay, this is probably a very naive example. So let's say we want to learn a federated learning model to do handwritten digit recognition. Then Google can, for example, ask its employees to write some digits and manually label them. And then Google can use that data set as its training data set. Does this make sense? So basically, the idea is the server is usually some service provider, right? Like some big company. Those companies, they have employees. They can ask their employees to manually label a small training data set. And our evaluation shows that this server's training data set just can be very small. Okay, the server does not need to collect a huge training data set. The server just needs a very small training data set, so it can manually label that data set by itself. Yeah, does that make sense?
Yeah, that clarifies the things. I was actually thinking of having the ability to also bootstrap from the clients to get something that is a little more representative of the big wide world. But your perspective makes it a little cleaner rather than getting into the space of the client. So thank you for clarifying.
Yeah, okay. Thank you for the question.
Of course.
Yeah, let me see. I think Q&A has 2 more questions. Okay. One question, does the bounded number of malicious clients determine the probable security level M star? Yes, exactly. Actually, so the M star, so I should make it more clear. For any number of malicious clients, we can derive the certified security level M star. But if the number of malicious clients is larger than some threshold, the M star will become basically, the M star will become basically 0 something. Yeah.
Meaningless.
Right. Yeah. So the next question is, what is the overhead introduced by the ensemble setup? Yeah, this is also a good question. So the question is, because in our ensemble federated learning, we train multiple global models. Okay, so one question is, what is the overhead to train these N global models? So if we, so I should say there is a trade-off between the overhead and the probable security. Okay, so why I say that? Because see, now I train N global models, but I can remember the federated learning is an iterative process. Let's say originally when I train just one global model, I use 1,000 iterations. Okay, so this will introduce some overhead, right? Communication cost and the computation cost for the client. Now I train 10 global models. However, when training each global model, I just run 100 iterations. Okay, so I run less number of iterations when I train each global model, such that the total cost, okay, the total communication and computation cost may be the same as training one global model. But when we do this, we may get a smaller certified accuracy. Okay, so there is a trade-off. If we want to have a larger certified accuracy, we may train more iterations for each global model. Okay, so I hope that answers your question. In part, so one more question. In part 3, do you have any recommended strategy for choosing the groups of clients to train each of the local models? Or do you just pick the groups uniformly at random? Yes, in order to, at least for now, in order to derive the certified security level, we have to pick the groups uniformly at random when training the global models. Yeah. Yeah.
Okay, thanks, Neil. That was a great talk.
Thank you, Mike.
So I just want to remind our viewers that we do this seminar every Wednesday this summer at 1:30, and you can go to our website at cerias.purdue.edu and find this video pretty soon in the next couple of days, and any video that we've had in the past, going way back, like almost 20 years of security seminar videos. So thanks again, Neil. Take care.
Yeah, thanks everyone. Bye.
Bye.